Okay, guys. If people still got pad and paper, that's fine. A prompt question on here. What types of stars have you heard of? What is the difference between them? So this picture obviously gives us some clues. Has anyone got any responses to that?
Well, I know different names.
Yeah?
Like, there's a supergiant, there's a hypergiant.
Yep. Good.
I can't remember the different names for the different colours of stars.
I mean,
it's just the colour, isn't it? Like red giant is.
Yeah, it's true.
Just red giant and blue giant.
Good. So yeah, I mean we've covered lots of things there. We've got different colours, and we've got different.
The dwarf stars.
Say again.
Dwarf stars.
Say again a bit louder.
Dwarf stars.
Dwarf stars. Yes, good. So we've got giants, we've got dwarfs.
Can I include neutron stars?
You can mention neutron stars, absolutely. Neutron stars we will talk about quite extensively, but not right now. Okay. They don't really fit in very well with the categories and the ways of categorizing stars
that's true.
We're doing here. Do we know anything about neutron stars?
Yeah, the fact that they're just made from neutrons and they're like the densest stars you can get.
They're very small.
Yeah, exactly.
And they spin really fast.
They
can spin fast.
Certainly can spin very fast, yeah, good. So they're incredibly dense, incredibly small, Sam, like you said. So given, looking at this diagram, looking at the sun, the sun would appear to be a pixel, so a neutron star just doesn't work on this scale at all. So we won't mention it right now, but yeah. Does anyone know anything in between a dwarf and a giant?
The sun.
Yeah.
I don't know the name for the sun, though. Is there a name for the size of the sun?
Yeah, there is. But yeah, you're right in that like there are really small stars and really large stars. And this diagram seems to suggest that the sun is tiny, but actually on the scale of things, the sun is kind of normal sized, not particularly giant or particularly dwarfy. It gets confusing in astronomy sometimes. Like technically, there are ways of classifying stars that would classify the sun as a dwarf. We kind of ignore those. So the system we're going to start having a look at to begin with, if I can get my PowerPoint to go forward here, is called is basically the fact that we have different names for different stars depending on how bright they are. So we don't have to know details like it's called the Yerkes or Morgan-Keenan classification system. Basically, we're just grouping these based on how luminous, how bright they are. There's a slight difference between luminosity and brightness, but it's basically the same idea. And hopefully you can see on the diagram on the right, there's different shaded areas. Don't worry exactly what the diagram's showing, but just realise there's different shaded areas that have different Roman numerals associated with them. And each of those groups have a name associated with them as well. Generally speaking, the brighter ones, the more luminous ones, are higher up. So, like you said previously, Type 1 supergiants, sometimes called hypergiants for the brightest ones. Obviously, things kind of change over time. So the Type 1 was split later on into different subtypes. So we've got supergiants, hypergiants, bright giants, etc., etc. Or rather, bright giants are Type 2. Giants, Type 3. Type 4, subgiants. You don't have to know exact details of this. Just remember giants, dwarfs, and then the part of this classification system where the sun comes in is the main sequence. Okay, if we did GCSE triple, that should be vaguely familiar to us when we did stellar evolution. So main sequence stars, like the sun, are where the majority of stars spend most of their life. So that's that V, that curvy band in between. Again, don't worry too much about the diagram. We'll come back to it later. So yeah, this is how we split up stars and classify them based on how bright they are. The MK system. Dwarfs, main sequence, giants of various sorts. Everyone good with that?
Yes.
Mm-hmm.
Good. Pretty straightforward, right?
Mm-hmm.
Yeah.
Good. So, little tweaks to this. We've talked about brightness before when we were talking about the Hipparcos scale and how bright things appear to be. The only problem is the brightness is kind of a subjective thing. It depends on who's doing the observing. So our eyes only see particular wavelengths, but stars can output different wavelengths that don't correspond to what our eyes see. So luminosity is the more general idea. It's the amount of energy being emitted by the star in all wavelengths, all types of energy that's being emitted in all directions. So it isn't just visible electromagnetic radiation. It's also ultraviolet, X-rays, infrared. It even includes things like neutrinos and stuff that aren't even photons. But most of the energy is emitted as photons. What do you think the luminosity of a star depends on?
Heat?
Where it is in its cycle?
So, yes, its life cycle will change its luminosity, but I guess, like in terms of thinking of it mathematically, there are things that are changing during its life cycle that cause its luminosity to change. Joe, heat,
is it the type of fusion it's out giving?
Heat is a word that we need to be very careful with.
Should I say temperature?
Yep, definitely. So yes, it depends on the temperature of the star.
What kind of gas it's fusing with?
Yeah, so again, lots of different processes happen during its life cycle. So yeah, what fusion is actually occurring will affect its temperature, for example, but it will affect one other thing. It's kind of really obvious if we go back to where we started. Say again?
The mass?
Very close. Very, very close.
Color?
Yes, the mass affects this.
The radius.
Did someone say something? I think I heard it.
Radius. Of
Exactly.
the star.
How big the star is, its radius. So, a larger star will emit more radiation. A hotter star will emit more radiation. Mass will affect both of those things. Obviously, it affects size. And we have to remember as well, the more massive a star is, the denser it will probably be. So, there won't be a linear relationship between size and mass. And yeah, depending on what type of star we're talking about, it'll have different processes happening. So its temperature could vary enormously depending on what's happening there. Which we've already kind of mentioned when we talked about the different colours of star, which we'll get onto in a second. So luminosity depends on size and temperature, but it specifically depends on the Stefan Law. So this is something that we do need to be able to use. And it looks horrible, but it's really not that surprising. Luminosity is equal to 4 pi times the Stefan constant times the radius of the star squared times the temperature to the power of the 4. Okay, it looks horrible, but it's really not. 4 pi, and then there's that sigma, the Stefan constant. That's just a number. So luminosity is proportional to radius squared times temperature to the power of 4. So if I double radius, my luminosity will go up by a factor of 4. Interesting though, if I double temperature, then my luminosity is going to go up by a factor of 16. You said optimistically, is that correct? 2, 4, 8, 16. Yes. So the biggest effect on luminosity comes from the temperature of the star. And obviously this is a 3-variable equation. The way this would come up in a question would be, it would give you temperature and radius and ask you to work out luminosity. It would give you luminosity and ask you to work out and temperature and ask you to work out radius. The most subtle questions that could come up is ones where they say that you have 2 stars of similar absolute magnitude. So that was saying similar luminosity. It doesn't tell you what it is. It doesn't let you work out the luminosity, but it says it's similar. And I'll give you the radius of one, the radius of other, the temperature of the one, and ask you to work out the temperature of the second one. I believe there are some questions like that in the question paper I put up. So we'll go through that when you've had a go at it. So basically, just think, how many variables are there? What do I know and what don't I know? Sometimes you'll be comparing stars. But it's just a pretty straightforward equation.
Sir?
Yeah.
What are the units for all of these?
Good question. So luminosity is in watts, radius is in meters, temperature is in Kelvin, and then we can work out what Stefan constant is in, because I definitely don't remember it off the top of my head. It will be in watts per square meter per Kelvin to the 4. But I'd be surprised if they ever ask you to tell them what the actual units of the Stefan constant are, especially because it's given to you on your data sheets. So, you can just look at that if you need to.
Mm-hmm.
So what this means is that more temperature means more energy is emitted, and the larger the star, the more energy is emitted. I threw this diagram in because we're going to refer back to it quite a lot. You might recognize this, again, if you did triple GCSE, as a Blackbody curve. And basically, this is just showing how the amount of energy at each individual wavelength changes. So the black line, the 3,500 Kelvin star, that's showing how much energy is being emitted at each wavelength of light. And you can see that as temperature increases, 3.5, 4, 4.5, 5, 5.5, the total area under the graph gets bigger. So more energy is being emitted. And you can see that it changes quite quickly. So 3.5 to 5.5 is not even close to doubling, but there's way more energy, way more area under that graph at 5,500 Kelvin than 3,500 Kelvin. So this is a way of visually showing the relationship between temperature and luminosity. Okay, so for those of us who didn't do triple at GCSE, we need to understand what a blackbody radiator is. And a blackbody is, well, I mean, I guess it's obvious, something that is perfectly black. So if you cut something in Vanta black, then it's pretty close to being a black body. And basically, it absorbs all of the light that hits it. We can think, okay, this would be a problem, conceptually, if it didn't also emit all of the light that it needed to. Because otherwise it would just heat up and up and up and up, because it's a perfect absorber. So it emits all of the light, the same amount of energy as it absorbs, but absorbs all of the energy that hits it. So there's no such thing as an actual black body. There are lots of good ways of approximating it, like a cavity, like a box covered in black stuff, like black paint, is a pretty good attempt at a black body. But even a star is an okay, an adequate model, an adequate example of a black body. And there's a very specific shape of emission spectrum that you get from a black body. And we've already seen it today. It's that very distinctively shaped curve. And you need to be able to draw this curve. So, not for any particular temperature, but you need to be able to recognize its shape. So remember, at zero wavelength, and this is not a perfect diagram actually, at zero wavelength, if we think back to quantum, that would imply each photon has infinite energy. So there are no photons at zero wavelength. So down there near the origin, the line should be at zero. The amount of photons, the flux, should be at zero. And then it rises steeply to this peak, and then falls away gradually down towards longer wavelengths. Okay, so you need to be able to actually produce that shape pretty well. And again, we can see how the shape of this varies with different temperatures. We've already mentioned that the total area under the curve increases as temperature increases. Can we see what else is changing as temperature increases? Sam, what do you see?
Changing color.
It does. So there's this link between the color of something and its temperature. And that is fundamental. We talked earlier about the fact that you had red giants, blue giants, etc. Temperature and color are equivalent to each other, assuming these are black bodies anyway. And that's not too bad an approximation for lots of stars. So the higher the temperature something is, the bluer it is. The lower temperature something is, the redder it is. The way I think about this is if you take a lump of something, like a lump of metal, if you heat it up, it starts glowing, it becomes red hot. But if you carry on going, it becomes white hot. So the further towards the blue side you get something, the hotter it is. Good. George, what else do you notice?
The peaks are at different wavelengths.
Good. That's exactly it. So we can see there's a relationship between the wavelength of the peak and the temperature or the color of the star. So this relationship is really, really important. And again, we'll have to be able to calculate the relationship, calculate wavelength from a temperature and vice versa. And this is the relationship that we need to remember. It's called Wien's law. So we had Stefans Law, or Stefan-Boltzmann law before, that related luminosity to temperature and radius. Now we have Wien's law. And this is relating the wavelength of the peak of the spectrum to the temperature. And does so via this constant, which is known as Wien's constant, which is 2.9 times 10 to the minus 3. That is not millikelvin. Really, really, really easy to look at that as millikelvin, but it's not. It's meter kelvins, because you've got a wavelength in meters multiplied by temperature in Kelvin. So 2.9 times 10 to the minus 3 meter Kelvin. And that means that if we know the wavelength, we know the temperature. If we know the temperature, then we know the wavelength. We can work out one from the other. And this explains why we have this change of color as we get different temperatures. So if we look where most of the energy is being outputted for a cold star at about 3000 Kelvin, well, most of it's actually in the infrared. But it means there's more red than there is blue. So that's the graph on the left. So it looks red. There's significantly more. There's like 4 times as much red as there is blue. So it is a red star. If the peak is somewhere in the visible spectrum, so you've got something like the sun, which is at about, I'm not going to tell you exactly what it is, but about 6000 Kelvin, then you have a star with roughly equal amounts of blue and red. So it's yellowy white. Sometimes we call this just a yellow star, though. And then if you've got a really, really hot star where the peak has gone outside of the visible wavelengths, it's actually outputting most of its energy in the ultraviolet, then you've got more blue than you do red. So it is a bluish white colour. So this is what you get for something like a blue supergiant. More blue than red, therefore a bluish white colour overall. So that's why temperature is linked to colour. Okay, I'd like you to have a very quick practice with this. What is the sun's surface temperature? Its peak wavelength is 500 nanometers. I'd like you to, if you've got a calculator to hand, see if you can work out the temperature of the sun. I'll give us, let's say, a minute to do this.
$5,800 meter Kelvin. Meters Kelvin.
So you've got meter kelvins, but remember you're multiplying it. You're dividing it by meters. I'm looking for a temperature. So you get 9 out of 10 for that, Sam. 5,800 Kelvin.
Oh.
Okay. So yeah, we've got meter kelvins divided by meters because that's the unit for the wavelength at which the maximum amount of energy output. So I do need you to remember this number because you are expected to know details about the sun. And I said that there are approximately black bodies. That's an approximation. It's about 5,800 Kelvin, roughly. But the question that you are given in the exam might change that on purpose to check that you're actually doing a calculation. So it might give you something that gets a temperature of 5,750 Kelvin or something like that. So remember this to sense check everything, but don't just automatically write it if you're asked for the temperature of the sun from a calculation. And the reason I say it's approximate, you don't have to know this concept for A-level, but I feel like it's important to mention, is that I said that stars are like black bodies, but they're not perfect black bodies. So the sun has got like a spectrum that's that yellow part of this graph. The black body that would have the same amount of energy output is that grey shadow behind it. So it's not exactly the same, but they have the same area underneath the curve. And that effective temperature for the sun, according to this source anyway, would be 5,777 Kelvin. So it's not a perfect black body, so the concept doesn't work perfectly. It's not the same as sticking a thermometer into the sun, but it's a way of estimating the temperature pretty decently by using this concept of effective temperature. Anyway, that's just an aside. We don't have to know a lot about that. We do need to remember Stefans Law, Stefan-Boltzmann Law, and Wien's Law. So this is a spectrum from a real star, and first of all, it's obviously not exactly the same as a black body. It's got a similar sort of shape, but just like the sun is, there'll be some variations. But hopefully you can see some like really big differences between the ideal black body curve and this one. Clearly, there's some big old spikes and big old dips at different points in here. And we have to be able to explain that, and we can actually use these variations, these ways in which the star isn't like the ideal, to actually classify stars. Because we have these emission lines and these absorption lines. Now we have briefly covered this when we did quantum, I think it was. I remember that James gave a short presentation about how we did this, but we're going to cover it again now, just for clarification's sake. So a black body spectrum is like a rainbow. It's a spectrum. It has every single wavelength. Not necessarily at equal intensities, but they are continuous. But if you put a cold gas in front of a hot black body, which is actually what you have when you've got the outer layers of a star, they might be 5,000 Kelvin, 6,000 Kelvin, but they're still cold compared to the core, then it absorbs specific wavelengths of light. It re-emits them, but it re-emits them in every direction, so they're dimmer. So what you get is you get an absorption spectrum with these lines in it where light has been absorbed. And each individual star will have its own absorption spectrum. So it's like a fingerprint. And every element that is in that star will have a specific absorption line. So if you look at the spectrum, you can say, I know what's in there. If you look at how much light has been absorbed from each of these lines, you can say, I know how much of that there is there as well. So in this spectrum here, I can say, well, clearly there's some calcium there, because I can see calcium absorption lines. There's iron, there's magnesium, there's oxygen, there's hydrogen, there's sodium. We can tell what's in a star by looking at its spectrum, basically. It's like a fingerprint. And again, exactly the same concept here, just showing the absorption, or in this case actually the emission lines for specific elements. So if you see these patterns in the spectrum of the star, you know that element is present in a significant amount, significant proportion. And then when you look at the spectrum like we did before, you can see that these absorption lines correspond to the different wavelengths of light. And that lets us work out exactly what is in the star, basically. But, and this is really, really important, there is a relationship between what we see, what elements we see when we look at the star, and the temperature of the star. And this is not obvious at all. But what we have in the atmosphere depends on how hot the star is. If the star is very, very, very low temperature, then in its outer layers, then you might actually have molecules or just neutral atoms. So, for example, you don't have to know this, but titanium oxide will exist in the atmospheres of small, or at least cold, stars. So that lets us say, okay, whenever we see titanium oxide in this fingerprint, in this absorption spectrum, we know it's a low temperature star. So if we have lots of hydrogen and helium lines, then we know it's very, very hot. So what is in the atmosphere depends on temperature. So what we see in the absorption spectrum corresponds to how hot the star is. And that gives rise to this. And there is a lot of information on here. We do need to know a surprising amount of it. When we look at the prominent absorption lines, that's on the right-hand side of this table. When you see those specific things, you can say that the temperature of the star is roughly as it appears in the middle right column. We've already talked about Wien's law, so the temperature is related to its colour as well. And then the new part of this is the fact that you have spectral classes. And the spectral class is just looking at the absorption lines and saying what you have there. And we need to remember this series of letters, O, B, A, F, G, K, M. Has anyone got a nice, easy way of remembering a random collection of letters?
Oh wait, no, I can't remember the name of it. Sorry. What is the word you give every letter a random word and you make a sentence?
You do. It's a mnemonic.
Mnemonic. That's what it is.
That is it. So, this is the slightly less sexist these days mnemonic that we use. Oh, be a fine gorilla, kiss me. You can use girl or guy depending on your preferences if you would like. Gorilla is the extremely gender neutral and extremely weird substitution that you can make if you like. And it's a really messed up order. The reason it's messed up is that we used to use the strength of the hydrogen absorption lines from A downwards. And we thought that that was how we were going to classify stars. Before we had this idea of how the temperature dependence was between the absorption lines that we see and the colour or the temperature of the star. So we used to basically go A, I don't even know what the last one was. M is obviously the last one they use at the moment, but I think they might have gone beyond that previously. But now that we realise, okay, we're actually going to rank these in order of temperature, we go O, B, A, F, G, K, M. That is a decent mnemonic to use. If you want to come with your own, though, you always can. Good.
This is a Hubble Space Telescope image of the crowded core of the globular cluster Omega Centauri. The brilliant colors of the stars are real. They correspond to stellar temperatures. They can also be used to trace stellar evolution. Astronomers like to know how blue the blue stars are and how red the red stars are. So we'll first sort these stars out by color, blue on the left and red on the right. Next, we'll sort the stars according to brightness, the brightest stars at the top and the faint stars at the bottom. The final plot you see represents different stages of evolution of stars. Stars spend most of their lifetime burning on the main sequence. When the fuel starts to run out, they expand to become red giants. They find a new source of fuel, helium, and burn blue hot. But even that runs out. They end up burning out as white dwarfs. Based on images for the Hubble Space Telescope, we've assembled a true plot that is a snapshot of the life history of stars in this ancient cluster.
So this is a continuation of the live video we were doing earlier. I'm going to record this afterwards because my recording stopped when I pressed escape previously. So our Hertzsprung-Russell diagram that we were looking at in that video is something like this. And we can see that it shows along the x-axis the temperature of a star, along the y-axis its luminosity, its brightness. And it shows both the position instantaneously of a star on this scale, and it also gives some clue as to how stars evolve over time as well. We'll leave that, the evolution side, until next week though. You can see that the hotter, bluer stars are on the left, and the colder, redder stars are on the right. The dimmer stars towards the bottom, the brighter stars towards the top. Relatively straightforward, except that sometimes we get some strange things happening with scale. So we can look at some different Hertz Probe diagrams to get an idea about different ways in which we can present this information. So this is another HR diagram. We can see that luminosity, brightness on the y-axis, is done in multiples of how bright the sun is. And then our x-axis, again, has temperature. It has a strange irregular scale for temperature, but it shows those spectral classes along the bottom. O, be a fine gorilla, kiss me, from hot, O on the left, to cold, M on the right. Real data tends to look slightly different from the idealized version. So this is a Gaia, which is a space telescope that's done measurements of the luminosity and spectral class and temperature and color of hundreds of thousands of stars, if not millions at this point. And this Hertz Probe diagram is a bit compressed in the x-axis, but also a slightly different shape to the previous one. But we can still see the giants, the white dwarfs, quite distinctly. On this, the yellow or white colour shows there's lots of stars at that point. The black shows that there's not many, or there's individual pixels. So when a pixel lays on top of another one, it becomes red and then yellow and then white. So comparing these two, we can still see that main sequence band across the middle, and then that horizontal giant branch going across the side. But again, we look at this. Along the x-axis, BP, RP colour, and on the y-axis, absolute magnitude. So we've got completely different units for our scales here as we do here, which can be confusing. When you're measuring how bright something is, you can do absolute magnitude, you can do luminosity in watts, you can do luminosity as a multiple of the sun. When you're doing how hot it is, you can do temperature, colour, according to like some traditional system, actually a description of its colour, BP minus RP, don't even know what that is, and spectral class. Lots of different options. But at A level, these are the ones you need to know. Absolute magnitude goes from minus 10 at the top. Remember, absolute magnitude is an inverted scale, so minus 10 is a very bright star, to 15 at the bottom. And then your x-axis will either be temperature, 50,000 to 2,500, from left to right, or spectral class, O, B, A, F, G, K, M. O, be a fine gorilla, kiss me. You do have to remember that mnemonic so that you can recreate the spectral classes in order without any gaps. We need to refer back to the table to remember the exact temperatures of everything, but one way that we can try to remember this is that the sun is a G2, so that's just to the right of the FG boundary, and it has a temperature about 5,800 Kelvin. So G goes between about 5 and 6,000. This is the table that gives us the boundaries between the spectral classes. So the boundary between O and B is at 25,000, for example. The boundary between B and A is at 11,000. The boundary between A and F is at 7,500. It's a very common question that you'll be asked to sketch a Hertz Probe diagram. So you're looking to, don't use dots, just draw areas in which you'd expect to find it. The main sequence being this double curve, steeper on the left-hand side, flattening out, then steeper again on the right-hand side, and then your giants and supergiants are going to be horizontal blobs towards higher luminosity but lower temperature. Blue giants do exist, they're the ones on the top left, but they are going through a different evolution to a normal star. And then white dwarfs down on the left bottom, so low luminosity but high temperature, because they're very small. Remember Stefans Law, you can have low luminosity if you have high temperature, as long as you're very, very small. Hopefully that clarifies everything there. Use this information to try to complete the questions on Teams. Thank you.